Okay, before we start, number one, wear your safety glass. Okay, when you have safety glass, if you put it on your hand, doesn't do anything. You have to put it on your hand. Okay, good. Everyone has safety glass so that I can turn it on. Okay, number two, what we have inside is just oil and water. Just oil and water. It should not go into your eyes or anything. I test it, everything is fine. But if it flash, it goes into your eyes, we have the eye wash over there. So in case that thing happens, you open this, put your eyes in here, okay, and clean it. Alright? Okay, now we can start. Let me turn it on first. This is a separator. I turn on everything. It has a flow, okay, and it tries to separate and water and oil. Okay. Number one, I have to ask everyone, including you. How about that? Okay. In here, can you right? Can you look at inlet diverter? Where's the inlet diverter over here? Do we have it? If you have, where is it? Come closer. Where is it? Inlet diverter. Okay, that is the inlet diverter. You see the inlet diverter? Inlet diverter is to change the flow. Okay. Number two, oil bucket. What's your name? Hayden. Where's the oil bucket? Go point on it. Point on it. This one? Okay, that's correct. Water bucket. Next one. Which one? Want to do it? What's your name?
Zach.
Zach. Where's the water bucket? Where? Look in your information sheet. Oh, this one. Okay. This water bucket. Okay. Mist extractor, we should put it like over here, but this unit, they have it there. So it doesn't work as a mist extractor. It's like used to break the wave. Okay. Mist extractor, it should be near to the inlet. Pressure relief valve. Inside, in the info sheet, you don't have pressure relief valve. Okay, next to Zach. What's your name, sir? Eric? Come here. Eric, come here. Where do you want to put the pressure relief valve? If you need pressure relief valve, where do you want to put it? You want to put it here? Location A. Over here. B, C, D, E, F, G. Where do you want to put it? Pressure relief valve. The purpose of pressure relief valve is that if you have too much pressure, the separator doesn't explode. The pressure, excess pressure goes through the pressure relief valve. Where do you want to put it? Over here? So if I put mist extractor over here, you cannot put pressure relief valve over here, right? Do you want to put it here instead? Good? Yeah? Oh no, this is not good. Let's say I have mist extractor over here, I put pressure relief valve over here. Or do you put it over there? Which one? Here or there? Wrong. But still wrong. You have to put somewhere in the separator. The reason is that if anywhere get plugged, so let's say mist extractor get plugged. You see your picture? If the mist extractor get plugged, the pressure reliever should see the pressure and it relieves the excess pressure. And if you put it over here, and maybe over here is maybe fine, but we prefer to put it inside. Okay. The way separator work is, it uses the different intensity to separate two different kind of fluid. If the fluid have the same density, separator doesn't work. Okay. Inlet diverter help. Okay. The way that inlet diverter help is that when mixture hits with inlet diverter, what happens is the one that have more momentum, it has a difficult time to turn. The one that comes with less momentum can turn easier. So water have more momentum compared to air, right? So air will easy to turn, but water doesn't. So when we have inlet diverter, the change in the momentum help to do the separation. Okay? And when it goes inside, we have this layer. Okay? This part is the separation part. How long should it be? Should it be very long or very short? Of course, if you have longer, it's more expensive. Okay? In this case, it should be long enough so that it can do the separation. Just that. Everyone can locate oil bucket, water bucket. Before I turn it on, I want you to see the figure 5-4. See on the first page. You have oil layer, water layer on one side, and another side is just water layer. So this side is just water layer. The next person. What's your name? Obu. Which one is taller? This side or that side? The one with oil water? The level, the top level, which one is taller? That one is taller? Use ruler. Put it here. Like this. Yeah, that level. What do you think? Is the side that with oil water is a little bit taller? Everyone agree? It looks the same as in the picture, right? If you see the picture, the side that have oil water is a little taller. Okay, thank you, sir. Okay, next. What's your name, ma'am? Claire. Why is that? Why do we have this side is taller than this side? Why is that? I separating as I go down. Any other reason? Level is changing as I separate everything else. I don't quite like your answer. Does it have anything to do with density? You see this page? Can you explain it in terms of density? Yeah. The reason that the level height, they are not the same, and you can see that this side is taller than that, right? It's because of the difference in density. Can you explain it in terms of difference in density? Density has anything to do with this or not? Yes or no? Yes. Who do you want to help you? Anybody? Point one. Do you not want to point to anyone? Come with me. Okay, let me help you.
Words over here.
When we have this part, look at this. We have the liquid part connect, right? This part go down and it connect. So this means at the same level, it has to have the same hydrostatic head. Hydrostatic head is rho GH, right? On this side is rho GH plus rho GH. On another side is just rho G and H, total H. So if you do the math is next page. You can rho GH. So the equation that you have is rho oil H oil plus rho water H water, which is on the side that you have two parts, equal to rho water and H water prime. Okay, H water prime dictated by the rear height. This rear height. I can change it by moving up down. Who want to do it? Okay, next. What's your name? Jeremy. You want to change these things a little bit up or down? Yeah, just screw it somehow. What are you doing? You leave it up? Can you lower it down? So when you go down, take a look on this side. Anything happen? Down more? Or that's the maximum that you can do? You do a little bit more. Lowering it down a little bit. I think I cannot do much. Let me press it down. I'm afraid that I break it too. I raise it up. and up a lot more. And I didn't open anything yet. What do you think, Jeremy, what do you think happened if I turn it on? Anything change on this side? Which one become more?
I would say all.
You would say on or both? Let's try, let's try. Thank you, sir. I turn it on. It will adjust itself until hydrostatic head on both sides the same, just that. Okay, there will be the change in layer, and I think it may not do a good separation anymore. Maybe the height on this side may be too high, and whatever I do on this side, it cannot. It can actually. I think what happened is the layer of oil gets thinner, 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 so that the right hand side get more hydrostatic head to the level that the left hand side is the same as right hand side. Okay, I think we can do the math later. Now let's take a look. In the real field, we have automatic valve, the dump valve. Dump valve open and close this thing, right? Right now, I have it open all the way, all the time. And that is not good because gas go in here. I want gas to go up, liquid, just oil go on this side and water go this side. So the way it works in the actual field, we have automatic dump valve, open and close based on the hydrostatic head. And okay, at this point it should close. And let me turn it on. Okay. We still have good separation. The way that separator work is everything should be slow, no fast movement. Okay, but if everything just go to the separator, it can cause a problem, upset the separator. And we don't have enough volume to separate it. Okay? I want you to see some kind of vortex. Okay, when the liquid height is high enough, I open this valve and that valve. So only oil go from oil bucket, only water go from water bucket. What if, okay, let me close it down. You may see the vortex, gas rotating, and that's the indicator. You touch something?
No, it was my watch.
Ah, your watch, okay. It could be, okay, look at this. Right now, we have some kind of vortex, okay? It is the indication of vortex means you can see, I think I have to show the slides again. I open oil, pump, I flow just oil go to oil bucket. There's a separation over here, but if you can see here, okay, one of you, do you want to come? Do you see air in oil lamp? Does it have a hole? When you look from the top, does it have a hole? It looks like a hole, right? So it's not completely filled with oil. There's air inside. What about this line? Do you have air inside? What is that? Yeah, it's half full, right? So this means gas going here. Not good. So we should close it before gas goes inside. Right? Perfect. Yeah. Okay. The calculation. Okay, now let's talk about the calculation part. You do it by yourself. Okay, it's 1.1, 1.2, 1.3 is very easy. Okay, you can do it. I'll post a solution and we don't grade it. You just get one net and I test you later. Good. Okay, one of the questions. Do we have emulsion over here? Have you seen emulsion? Like in water, check and it doesn't separate. It is difficult to see if we have emulsion or not inside. What can happen is top layer is just pure oil. Bottom layer is like pure water, but in the middle is like a combination of both. Okay, let me turn it on and have each of you come take a look for a while. Oh, what's your name? Emma, can you open the valve so that we don't lift this thing up? And open this one. Which one should you open, Emma? Anyone that is too full, right? If you have too much water, we open that, so we drain water. And we may drain oil. So right now, it was just like, who cannot see it? Anything is something, can you see it? See how it works. Okay, what I want you to see, another thing is, Emma, you have to close it. It's too much, right? Now you have gas burner, you see that gas? Yeah. Too much. I cannot have one person open and close the valve all the time. So in the field there is an automatic valve. Okay, on this side, I want you to see the droplet. Okay, go take a look at the droplet on another side. Just go take a look. Go take a look on the droplet on the left side. Go take a look. There will be the droplet of water and oil. If you have seen it already, you may give another chance for other people. After you see it, please go back to your position, okay? So I hope each of you can see water droplet. Not good. Open it. So water droplet on the side. Oh, let me see that it moves. There's nothing wrong. Okay, that's good.
Pressure.
When we have water droplet on the side, the droplet comes when there's a mixing. Small droplet is not good. Okay? Small droplet make it more difficult for the separation to happen. Task 2. In the lab, we need a level controller, of course. 3.1. Estimate the actual volume we later use in the separation of oil and water mixture. Do not use the whole separator volume. Okay. Did you do it? Did I answer? What's your name? Olivia? Olivia, okay. Olivia. Where is the location that you have the separation between oil and water? Where? Which volume? Is it the whole separator? No, not the whole separator, right? Just the part that you have oil and water together. This volume. How big is that? How many liters? How big is it? You need a calculator? Okay, tell me conceptually, how do you calculate this volume? What length do you need? That length? Okay, what else? You need to know the height, the diameter of the pipe, and then we can calculate the volume of this part, right? Okay, thank you. I would like to emphasize on the volume for the separation of oil and water. Even though my separator is big, but the actual volume that is used for this separation is just this part, okay? Just that part. What happens is this: when we have small droplet, the worst thing that can happen is oil droplet. When it hits over here, oil droplet sink to the bottom. Okay, oil droplet sink to the bottom, right? And oil droplet has to move to the right hand side. It keeps moving, right? Because of the flow. By the time it moves, it floats up due to the density difference, right? So oil droplet. In the worst case scenario, oil droplets stay at the bottom. it moves to the right and it go up. If we don't have enough volume, first of all, if we don't have enough length, this length is not long enough. Let's say it's very short. So oil droplet move up just a little bit, and then it go underneath this and reach water bucket. That's not good, right? Correct? We don't want oil in water. So if we have some small oil droplet can move from the bottom, and it doesn't have enough time to separate, so it goes into this part. Another possible way is that if we have everything come too fast means we have a lot of water come, a lot of gas, maybe a little bit of oil, because we have high volumetric flow rate of liquid. So water can carry oil droplet to move from that point and reach water bucket. It's not good, right? So this means we have to have enough length. What about cross-section area? You see, the section that separates oil and water is just this part. If you look from the side, the cross-section area is look like a half circle, right? It looks like half circle. Okay, next. You right? What's your name? Paul. If I have the diameter, larger diameter separator, so this means we have larger cross-section area. What happened? Is that better? Is that help the separation? Okay. So intuitively, if we have larger diameter, we can handle more liquid. Does it make sense? I don't have to teach this, right? Okay. Why is that? Let us take a look at this. Okay. I ask myself, what is the velocity of the droplet travel from this point to that point? And I cannot calculate. I can estimate it. I can say, hey, total liquid flow rate divided by cross-section area equal to average velocity in the horizontal direction. Make sense? Total volume liquid flow rate, Q, divided by area equal to horizontal velocity. So cross-section area that I'm talking about is the bottom circle part. Okay. So velocity equal to Q over A. Right? So if we have large cross-section area, the average velocity of moving to the right-hand side will be slower and slower and slower. When it moves slower, this means it spends more time in this part, then it can separate better. Okay? But another question is, how long that is need to spend the time in this part? So you can have water droplet on the top. Water droplet will sink, moving down, right? The question is, that water droplet that's there on the top surface, when it reaches this point, we will have enough time to separate or not. We calculate it by using stroke law, equation 3.3. 3.3 stroke law. Stroke law is used to estimate the terminal velocity of water droplet in oil water emulsion or vice versa. If you see Vt, terminal velocity, equal to some constant multiplied by delta Sg, difference in specific gravity, multiplied by d sub m squared divided by mu. So if terminal velocity is a lot, this means it just takes a little bit of time to separate. Make sense? So if I give terminal velocity is 1 meter per second, I give it 1 second, then it can separate 1 meter. So high terminal velocity is good for separation. Look at delta Sg. Delta Sg is the difference between oil and water density. If delta Sg is 0, this means regardless of what we try to do, it doesn't separate. Terminal velocity is 0. It doesn't move, it doesn't separate from each other. Look at dm. dm square, dm. Okay. Alright. What's your name, sir? Will? What is the unit of dm?
Droplet size.
Yeah, droplet size. What is the unit? Meter? Feet? How do you know that? It's on another page, right? So this FM is micron. Okay, next, what's your name? Scott. Big droplet will separate faster than the small droplet or what? Why is that? Do it have more terminal velocity, higher terminal velocity? Go back to the equation one more time. Vt. So if the droplet is big, Vt go up or Vt go down? V sub t go up or V sub t go down? This one. You can look at my paper. Yeah. So if the droplet size is, for it, we have bigger droplet. Terminal velocity is high, so it separates fast. Okay. The speed of separation is proportional to the square of the droplet size. Bigger droplet require less time for the separation. Small droplet has a difficult time to do the separation. What about viscosity? What's your name? Landon. High viscosity or low viscosity is good for the separation. The separation, of course. So if you want to find out, I have the Landon. If I have water droplet on the top, water droplet traveling through oil layer. What is that viscosity? Is that viscosity of oil or viscosity of water? Yeah. Oh, what did I put in water? Another. What did I say? What did I say over here? Viscosity of continuous phase. Continuous phase is the medium that the droplet moves through. So for the case that droplet move through oil, the continuous phase is oil. So that viscosity is oil viscosity. Okay. If we calculate the separation of oil droplet, let's say we have oil droplet at the bottom and it tries to move up. So this means we have oil droplet traveling through water layer. So that viscosity will be viscosity of water. And d sub m is the diameter of oil droplets. Alright. So now we can calculate the terminal velocity, right? What about equation to approximate d sub m, droplet size? Do I give that equation? Okay, next, what's your name? Carl. Did I give the equation for that? Can you read it? Okay, what is dm 1%? dm 1% is for water droplet size. dm 1% is the minimum diameter of water droplet to be settled from oil to achieve 1% water cut. Okay. So basically, if you use this equation to approximate d sub m, you don't get perfect separation. You have maybe you can still have 1% water cut or something, but it's a good to start. Okay, and the calculation detail we skip that. Okay, 3.4. Assume that water droplet travel downward at Vt. Okay, how much time that is needed for water droplet to have a downward displacement equal to maximum allowable oil in oil water emulsion layer thickness. The downward travel time is defined to be TdW. How much is TdW? How do I know TdW? The maximum time that is needed. Okay. We talk about water droplet, right? water droplet will move up. Okay. Step number 1, I need to know how much does it need to move up. Okay, go back to your first page. At the first case, water droplet should travel from the top to the bottom of the left side of oil bucket. The height of that weir is the distance that it should at least travel to be conservative. Okay, so on the left side, let's say the weir height is, the vertical is 11 centimeter. The total length is more than 11 centimeter, but the height of this part is 11 centimeter. If we have enough time for water droplet to travel downward 11 centimeter, this means it will be able to reach water bucket, right? But okay, let's say we don't have that much time. At least we need to know how much is the oil layer thickness. I measure the oil layer thickness and I get about 6 centimeter. Let's say oil layer thickness is 6 centimeter. So this means water droplet have to travel through that 6 centimeter. Okay, now we know terminal velocity. Terminal velocity can be calculated, right, from the formula. Delta Sg multiplied by d squared divided by mu, and we get our terminal velocity. Terminal velocity is it the fluid property or flow property or both? What's the name? What? Anyway, terminal velocity, is that the fluid property or flow property or both? Should be both. The d sub m is flow property. If we flow fast, the chance that it will have a lot of mixing is high, then we have smaller droplets, right? And delta Sg is the fluid property. Okay? So, but it is kind of constant. We cannot do anything. But we can get the terminal velocity. After we know the terminal velocity and we know the length of the oil layer, so the oil layer is 6 centimeter. So we have terminal velocity and we have the oil layer thickness. How much time does it need for water droplet to travel through the oil layer? How do I calculate that? Do I use how do you do it? What was your name? Ryan, how do you do it? How do you calculate the amount of time that is required for water droplet to travel through that 6 centimeter layer? Assume that velocity is known. To travel 6 centimeter through the oil layer, what formula do you do? What formula? Is that T equal to B over S or S over B? Do you agree with him? He don't know. You don't know. What was your answer? Okay, let me repeat my question again. Option 1, time equal to velocity over length. Option 2, time equal to length over velocity. Which one do you want to use?
Length over velocity.
What? Length over velocity. Okay. I think it's correct. I agree with your answer. So if we know the terminal velocity, we know the length, we can calculate the amount of time. Yes, sir.
I was wondering, so how long does it take to get to the terminal velocity? If we're assuming that the terminal velocity
There will be some error. Whatever we do here, just the estimation. For example, we say that the water droplet should travel through the 6 centimeter, right? So that is the layer that we think it should. But what if your oil layer is thicker than that? So this calculation have some error. It depends on the layer of oil. But my point is, if we know the layer of oil thickness, 6 centimeters, we know the terminal velocity, that length divided by velocity will equal to the amount of time that is required for the separation to occur. Okay? That is the time required for the water to separate. Yes, question?
If this didn't flow with decibels, how do we know the thickness of the glass?
Oh, we don't. How do we, the question is, if it is in a closed vessel, how do we know the layer of this oil? We have option. Option 1, we say that we don't. Option 2, based on the hydrodynamic calculation, you can go to page 2, right? Rho H plus rho H equal to rho W H prime. So the height of oil layer will depend on the weir height, or the difference between the weir height. Basically, if I know oil density, water density, and I know the weir height, I can estimate the oil layer. Make sense? Yeah, that's how we know. But if it is in a closed vessel, we cannot tell. But we can estimate it by using that formula. Okay, what about time required for oil droplet to travel through water layer? How long does it take? Did you answer anything yet? Let's give you answer question already. So what's your answer? How long does it take for oil droplet to travel through water layer? What do you need? What is the information that is required to do this calculation? What do you need? Length? What length? I have ruler. What length do you need? How long does it take for oil droplet to travel through water layers? What was your name again? Derek. What length do you need? Measure it. I agree with your answer. Measure it. Oh, he has question, and I think it is a valid question. We need the length. Should it be the vertical length or the length along the curve or what? What do you think? Vertical length, because our droplet move vertically. So this length. So we assume that there's an oil droplet on the bottom, and it requires some time to go through that water layer. And I cannot get it accurate, right? I think, okay, 10 centimeters. What else do you need? Let me give you some hint. Alex, right? Your Alex, Ryan? Oh, okay, Ryan told me that time is what? Length over velocity. You already have length. What else do you need? Yeah. Terminal velocity. How do you calculate that? I mean, what is the value of mu? We calculate for oil droplet move through water layer. It's moving up, right? What is that viscosity? Viscosity of oil or viscosity of water? Viscosity of water. Correct. What about dm squared? Diameter of water droplet. Yes. So once we know that, we know the time. Okay, we know the time it takes for move vertically. Does it have anything to do with us? The time that it takes to move in the vertical direction is the requirement, is what it needs. But how much time do we give it? Do we give it a lot of time or not much time? How do I know that? How much time? Okay, what's your name? Jason. How much time does the droplet spend with this separator? How do you calculate that? 1 day, 2 days? Whenever it's full? Okay, let me give you something. The amount of time depends on the separator is big or small. If it's big, it has a lot of time inside. And we can assume that droplet move like horizontally at the average velocity. How do you calculate average velocity? Average velocity, what I mean is, I know oil and water they mix together, right? Let me turn it on. Oil and water they mix together over there, and it moves to the right hand side at the average velocity. How do you estimate this average velocity? And we assume that the whole cross-section area moves in the same direction. How do you estimate the average velocity? Yeah, let's say velocity of, yeah. How do you calculate that? Velocity of water and oil, Jason, right? How do you calculate velocity of water and oil? Then it goes into this direction. How do you do that? Does it have anything to do with flow rate? If it flows fast, the horizontal velocity is a lot. If it flows slow, the horizontal velocity is less, right? Let me close it a little bit. Okay. Now we have it move like this, but slower, right? So it has something to do with this flow rate for sure. So velocity is volumetric flow rate divided by area. Yes, Jason answered right. One way of doing it is you say the velocity in the horizontal direction is volumetric flow rate of liquid part divided by cross-section area that the separation happened. You don't use the whole separator, but just the bottom part, because that's where the separation happened, right? We assume that the bottom circle move in the same direction at the same speed. Make sense? So with that, I can estimate the velocity when it moves horizontally. Okay? But how much time, Jason, you still didn't answer the question. How much time that the droplet spend inside? We know the velocity and then what? Do you need a ruler? Yeah. Time equal to what? Length divided by velocity. What length? Can you show me? You don't need to measure it. You just tell me which length. The whole thing? The whole thing? What length are you talking about? From this point to the end or what? I don't think so, because look, the separation occurs in just this section, right? So the time that you give it to separate, you should count only where separation happened. Where do we have separation? Only this part. Yeah, the length should be just this much. Oh, you said that. Okay. I'm sorry for that. Correct answer. So we have the amount of the length, right? If we have length divided by velocity, velocity is volumetric flow rate divided by area. The area is a cross-section area on the bottom part. Then we have the time, like length divided by velocity is the time. So it is the time that we give for the droplet to separate. If the amount of time that we give is more than what it requires, then it's good. But if we give short amount of time, but it requires a lot more time to separate, then we will see oil in water and water in oil. We don't have separation. Make sense? It doesn't mean that if we do know all this, we are done or something. In an actual separator, we may not be able to assume that. So right now we assume the velocity to be the same everywhere, right? But in reality, in the middle it moves faster. In the edge, it moves slower. So what do? How do we need to do experiment or something? What's your name? Alex? So our calculation is not quite accurate, but it gives a reasonable approximation. In reality, what do? How do we select the size of the separator? Anything?
Depends on the flow rate that you're going to have.
No. What wood do we use? The name of the book. Yeah. What is the name of the textbook that I upload on the blackboard? Did you download it? Maybe. Serious textbook. In that textbook, there's a chart. The chart is based on some kind of test. They tested already that this flow rate need to have this much, this tank diameter can handle what flow rate or something like that. So at the end, you use the chart. But we still need to know the terminal velocity, something like this. Okay, what's your name? Senior? Why do we need to know the calculation when at the end we just use the chart anyway? Maybe just because I want to test you or what? Where the separator? Okay. The input from Mr. Bullard is this. Not every separator is built at the standard size. It can be custom made. In subsea separator or non-subsea offshore separator can be other size that is not in the book. What if your separator size is not in the book? What do? You cannot do anything, you quit? No. But you have to know the theory behind it, right? What if the separator doesn't work? It doesn't work. You have three-phase separator, it doesn't work. What do? We trash it and buy a new one instead of, hey, we may have a little strange density, we should tell the weir height to be a little shorter. So if you know the calculation, you may say, hey, the weir height could be too high. That is a potential problem. Or you can detect, is this too short or is not big enough? Not everything is on that chart, but that chart covers 90%. 90% of the separator is that, but it's not 100%. When you have 10%, so it doesn't mean that you work for 9 days and then the day 10 comes, you quit. No, it's not like that. So that's why you need to know the calculation. I think we still have some time. 3 more minutes. Question for me? You may. Oh, okay. I didn't ask every one of you. You want to say something? What's your name? Steven? Do you like this one? It's cool. Can you turn on the water? Oil? Everything? Turn on everything? No. I have. Yeah, turn it on. Everything? Yeah. Everything. Yeah, everything. I remember everything. Okay, I have a question. Let it move for a while. I'm kind of a little bit more. Look in, Steven, can you look in water bucket? Is this a good separation? Yes or no? -1. -1. No. This is not a good separation. Okay, you can go back. What's your name? Daniel? In water part, is this a good separation? Yes or no?
Yes.
Because the water. And you can see air inside, right? Your name, next. What's your name? Tristan? Okay, in our bucket, is this a good separation? You see air bubble, right? So whenever air goes to this, it's not good separation. Who else is getting? Oh, you. What's your name? Taylor, come here, please. Is this 2-phase separator or 3-phase separator? I beg your pardon. No, you're not going anywhere. Do we have water? Okay, where's the gas? Taylor. This one. Okay, perfect. Connect. We may. You two, you don't have to answer anything. Did you sign with your name? It's 1:50 already. Thank you everyone for coming. I appreciate. You may go now, or you may stay around.